What do you guys want to look at? I was like, you guys got to get to drag this one.
On 4.6, or 17 part B and 19 part C, like the graphing part.
Yeah, the graphing part. So 4.6. Let's look at, what was it, 19? Which one did you pick?
Both of them, 17 and 19.
Well, let's just do one of them. So, let me look. Let's see which one I want to do. Let's go ahead and do 19. So we'll do 4.6, number 19. We'll do 19. I know I had lots of people that had hands up. Any other we want to pick out right now? I was just saying if anyone else wanted to chat one out right here while we're here. Totally fine. We can make that choice later. So let's look at 4.6, number 19. This one it's one of our variation problems. So I'm just going to write it out. We've got that R varies directly as L and inversely as the square of D. So the very first thing we need to do is we need to write this as a like expression, equation kind of dealio. So if we know that R varies, so that means R is kind of our boss. So we're going to have an R equals. So we've got directly as L. What are we going to do with direct with L? Yeah, we're going to have L just kind of be directly across the equal sign. It's right across the sign. If we are inversely with the square of D, what does that mean for us for it to be inverse? 1 over the square of D. So D squared. Whenever we have one of these, there's going to be some constant K. So you can either put times K. You could simplify this to have it be L over D squared times K, or KL over D squared. The way you mark it doesn't particularly matter. If I would 100% take L times 1 over D squared times K, I would 100% take KL LK over D squared, whichever way, and any combination therein. So we have lots of options on how we put it down. But that's all we have to do for part A there, is to write it as our, or express R in terms of LD and the constant of variation. That's this. It's writing it as the expression. For part B, they give us a little bit more information. For part B, they tell us that we have diameter of 0.01. We're given that the length, L, is 100. And they got the result, their resistance, R, of 25. So they're straight up telling us that in the problem. So we're going to use that to help us figure out what the heck our K is going to be. So we're going to substitute these pieces in so that we can solve for K. So we know our R is 25. And that's going to equal our length of 100 times our 1 over that diameter, our 0.01 squared, times that K. So if we substitute those pieces in, we can use that to solve for K. What can we do to simplify this thing? As I say, we could do some multiplication and stuff, right? I can simplify this. This is 100 times 1 over 1/100th squared. So you can either simplify our fraction, deal with this power. We can multiply these all together, type the whole gosh darn thing into the calculator. Whatever it is we need to do. We should, like, as we're working this through, we're going to wind up with 25 equals, you can do 100 over 0.0001. Okay, and simplify it like that. You could multiply both sides by our 0.001 and then divide by 100. We could divide by 100 and then do the multiplying. Whatever it is we want to do, however we get there to get our k by itself, we should have, I'm just going to double check. I want to make sure they put it as a fraction. I want to make sure that I'm right before I can just work it around, see what we get. Yeah. 0.000025. So it's 4 zeros and then our 25. That's what we need for part B, is to solve and get down to this k. Because we're going to use this and the information from B kind of to help make our graph they want for C. So we're supposed to sketch the graph of a relationship between R and D. So R and D are going to be my X and my Y. Since we already have this set up with R equals, that's going to be my Y. Since we already have an R equals, R is going to be my Y. And so they tell us to use D. That's going to go on my X axis. That is definitely meant to be an X. It looks like a delta. There we go. So for part C, we're going to be sketching our graph, which means those are the only two variables we want to have left. So they tell us some information. They tell us to use that L equals 100. And we have our K from part B. So L is 100, K is that guy, and we're going to try and make this equation. So we have our R equals our 100 times that 1 over D squared times that 0.000025. And we can simplify this a little bit because that's a mess. Gross. Where we have our R equals, and we can times our 100 and our 0.000025 together. So we're going to get 0.1225. 1 over D squared. Or you can put your 0.0025 over D squared. And that makes this a rational function. That makes this one of those things we were looking at when we were graphing our stuff in 4.5. 0.0025 over x squared. Because we're having R be our y's and D be our x. Now we can look and see where we've got asymptotes, where we've got ratios of constants, ratio of those leading coefficients. Finding those asymptotes. This is the same thing as 1 over x squared. So it's going to give us a rational function. So I'm going to change my page just a smidge. So when we go into graphing this and just trying to sketch our graph, where are we going to have asymptotes? What is the ratio of my leading coefficients? 0. What is the 0 of my denominator? 0. So our asymptotes are going to be at x equals 0 and at y equals 0. So we're going to have an asymptote right here and an asymptote right here. So we're just looking in these quadrants. It's our x and y axes that give us that. We know a little bit of information. We know when we have our length of 100, I have that resistance of 25. We know our diameter that was at that time too. My diameter was 0.1. So when I have 0.1, my R was 25. That gives me a point. Somewhere up here, we have a point because we know that when diameter and resistance were our 0.01, 25, I had a point. Admittedly, it is very, very close to my asymptote, if that's 1. But that's enough to kind of see what's happening because we know the shape of these graphs. They're going to approach our asymptote here, and it's going to approach our asymptote here. Can we have negative diameter? So we don't need to, for practical purposes, we don't need to graph anything in the negatives because we set our x as the diameter of this wire. I can't have a negative diameter. It's literally inside out, and it makes my brain hurt to think of the geometry of it. So we can't have anything negative anyway. If you want to plot a point over there, absolutely fine. We can plot a point for y equals 0.0025 over x squared. We can pick that up. Totally fine. But we don't necessarily have to. This gives us our sketch. The sketch is the sketchiest sketch of all. We do not have to do much with it. Mostly just noticing, is it linear or is it like a rational thing? The last bit of this question, because there's one more bit, was to make a prediction. So part D was to use our equation. We have some information. We know that the diameter that they're giving us is going to be 0.015, and the length is going to be 50. And we're asked to find R. So we know K, we know a diameter, we know 50. So we're going to take our equation, we're going to plug in our diameter, we're going to plug in our length, we're going to plug in K. And we're going to be able to make this prediction. And I'm going to change my page again. I'm going to shrink it in so you do not have to look quite so far out. So that gives us all of our information. So we're going to use our equation from part A, that thing we very first started with, where we're going to get our resistance, our R, equals whatever this length is, 50, times 1 over that diameter squared, 0.015 squared, times our K, that's 0.000025. The right side of my equation is all numbers. We can simplify it. We can type the whole gosh darn sucker in a calculator, and we can get that resistance. So it's just trying to put these variation problems into context. The graphing, sketching bit, do not stress too hard on those. It's mostly so that we look at the equation and see that that's a rational function. Sometimes we'll get linear. We might get a quadratic. More than likely, we will have a linear or a rational. When we type this into the calculator and we simplify it down, and you can just straight up type this in exactly as it is right here. What do we get? Yeah, 50 over 9. If you type it in the calculator with all the decimals, it probably gives you 5.55555555555. And we want to do our very, very best not to round our answers off. So if you get something super decimally and you've typed it into the calculator, hit the button that looks like 2 triangles. That'll switch you from the decimal mode into the fraction mode. And it should give you a fraction answer of 50/9. So that's question 4.6, number 19. Yes, ma'am.
Explain how did you get the asymptotes?
So our asymptotes, that's thinking to our 4-5 kind of information when we were looking at our rational functions. And just pulling up my list, make sure I don't say things crisscrossed. So when we are finding our asymptotes, we get our vertical asymptotes from the zeros of our denominator. So this comes from our solutions or our zeros of the denominator. So if we look at our denominator here, it's just x squared. So x squared equal to 0 is just 0. So then we'll have our vertical asymptote happens at x equals 0. Our horizontal asymptote, because we have x squared on the bottom and I have 0 x squareds on top, looking at that ratio of leading coefficients, 0 over 1, 0. So our horizontal asymptote comes from the ratio of those leading coefficients. Yeah. And then everything else is just like a point that we kind of pick and or are given. Again, I'm not going to stress super hard about the graphs. It's mostly just to say, hey, look at this shape. It's a rational function. That's why that's in this chapter. Because it feels very awkward to be in this chapter. What else do you guys want to look at? That was a good question. That was a really good one. Number 17 is very, very, very similar to that one. It's again, so you're going to write your equation, you're going to substitute pieces in. I want you guys to try 17 yourself. It's very much the same kind of vibe. So you're going to write your relationship, you're going to substitute in the information you know, substitute back in the information you know to get an equation. It's going to be a linear. And then you can make a prediction. So it's very, very similar. Use this one kind of as a guide for 17. But I don't want to do both of them, because I want you to practice it. What's up, Australia? 33 on 4.5. Let's look at that one. 4.5, number 33. And we look at that one. Graphing. So looking at this will give us a great practice on that one. So 33. There we go. I'm going to look. That feels very large. What else? Okay, so this is tells us to sketch as best we can. So 33, we have our f of x equals x minus 1, x cubed minus 4x. Why is this page such a bizarre dimension? What else? So this will kind of let us practice all of those things we were kind of talking about for the sketch in 4.6. I'm going to zoom back in because I don't like it being that zoomed out. What should we do first? Try and factor this. Because when we're working with these, we really, really, really need to have things as factored as we can get to see if we have any discontinuities here. So I can rewrite this. Our numerators are x minus 1. That one's not really changing. What can we factor in our denominator?
An X.
We've got an x. And that's going to leave us with x squared minus 4. Can I factor this more? Yeah, because this guy, difference of squares. So we can factor this even more. We've got our x minus 1 and x times x plus 2, x minus 2. So there's a lot of pieces here. First things first, do we have any discontinuities, like removable discontinuities, a whole? Nope, we don't. Because we don't have any terms that cancel out, no factors that cancel out, we do not have a removable discontinuity. So there is no whole here. So then let's take a look at where we might wind up with some asymptotes. So we can do, you can do intercepts here, you can do asymptotes. We know we're not going to have any discontinuities, so we can start in with those vertical asymptotes. Where are we going to have vertical asymptotes? That's where we're going to have our zeros in the denominator. Where do we have zeros in the denominator? 0, -2, and +2. So when we're trying to sketch this out or graph it, I'm going to draw it over here. I'm just going to kind of freehand this. Well, we know we're going to have a vertical asymptote at -2. That's this guy over here. -2. We're going to have a vertical asymptote at 0. Like this. Just so we can see it over there. And one at +2. So we wind up with a lot of asymptotes on this one. So there's our +2. Questions on those asymptotes? Just working in pieces here. Now let's see about our horizontal asymptote, or our slant asymptote if we have one. Is the degree of our numerator higher, denominator higher, or are they equal? The denominator's higher, so this one's what we call the bottom heavy. If we have a higher degree in the denominator, we will have a horizontal asymptote guaranteed. Where? 0. Because I have 0x cubes over 1x cubed. If we look at this original one, I have no x cubes over 1x cubed, so 0 over 1. Our asymptote's at 0. We can still think that ratio of our leading coefficients. So, oops, sorry. That's that ratio of leading coefficients of the same degree. So it has to be of the same degree. So we have 0x cubes over 1x cubed, so we're going to have our horizontal asymptote at y equals 0. So we're going to have our asymptote right there, right on our axis. So now we have kind of barriers on where we're going to have stuff. We're just going to have to figure out where everything is and what it looks like. So I might have a shape here or here. I might have a shape here, 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 or here, here. We have 8 kind of zones. What we're going to do is we're going to test some x values to get points to plot and kind of see what's going on. We know on these outside pieces, because of the way these are, rational functions are, it's going to have to approach both asymptotes, the vertical asymptote and the horizontal. When we're between 2 asymptotes, kind of all bets are off. The vertical asymptotes are still maintaining, like, they're not being crossed. But the horizontal asymptote, because that deals with as we approach infinity, the horizontal asymptote can be crossed in between. So we're going to plot up points to kind of see what's happening. And you can do that with a guess and check situation, typing things into calculator, just getting values. We don't have to do this in any particular way. If you want to go through and catch x-intercepts, y-intercepts, all that jazz, totally valid. But we can also just kind of plug chug in and put in f of 1, f of -1, and see what's happening there. We can substitute in at 3 and at -3 to see what's happening out on the side. If we want to do more and get 1/2 and 1.5, or -1/2, or -3/2, we can put those in just to kind of see where points are. But it's all just going to be kind of substitution in to check and see what's going on. I need a pen. So if we get like f of, just to start from the farthest right side, if we substitute in f of 3, and I substitute in 3 minus 1 over 3 cubed minus 4 times 3. And you can type that in a calculator. You can use the factored form, or we can use the original equation. We should get, I believe, 2/15. What that tells me is that over here at f of 3, we have a point at positive 2/15. It's going to be somewhere up here. That one point is on this outside wall is enough to let me know that it's going to approach my 0 here on my horizontal asymptote, and it's going to approach this vertical line here. So I know this shape is going to look kind of like this. Any of our outside pieces are going to look just like the normal kind of irrational functions. So it's going to approach my horizontal, and it's going to approach that vertical. So I'm substituting that 3 in place of x into our equation. We're just doing kind of a guess and check, because I've got my asymptotes, but I don't know what I'm drawing. When in doubt, pick more x's, plug them in, and find your y's that way. We can always plot up points. And we want to know what's happening between all of these asymptotes. So sometimes we'll have to plug a whole bunch of stuff in. And one of the benefits of using the yellow calculators is if you type it in, and then you hit up, enter, you can go back and edit what you had. So let me open my calculator and I'll do the negative one up here. Because I'm going to see what happens on the outside, just because these are my 2 easiest to draw. So let me do f of -3. And I'll show you how we can type that into the calculator. So when we're trying to do f of -3, and we know we've got this fraction here, I can put in my -3 minus 1. I'm putting that in place of the x, that -3. In my denominator, I want my -3 to the 3rd power. Got to hit that right arrow to get out of the exponent. Minus 4 times that -3. So I'm substituting the -3 in place of all the x's in my function rule. And so we get 4/15 for -3. 4/15. Which again means we have a positive value over here. So I can go whoop, whoop, and I know how those are going to behave. In between my 2 other sets of asymptotes, it can look linear, it can look quadratic, it can look cubic. It's going to have very similar vibes. It might look like one of them. We might have more than one. So we may have to substitute in more values. So if I want to see what's happening, we know what's happening at -2, so maybe I want to see what's happening at -1. The benefit of these yellow calculators, I can hit up, up, it highlights it, hit enter, copy and paste. Then I can just go back and switch out my -3s for, let's say, a -1. And I don't have to type the whole thing again. You can swap it out. Totally valid. So when we substitute in -1, we get -2/3. So at -1, it's down here. Yes, dear.
Just picking up any points.
Any point that's not on an asymptote. Because I don't need to substitute in -2. If I substitute in -2, it's gonna give me an error. If I substitute in 0, I'm gonna get an error because it's gonna divide by 0. So I'm just picking x values at random. And I can kind of see something happening here. Like I know it's going to approach my asymptotes, but I don't know whether it's approaching to the up or to the down on these two asymptotes. So I still don't know what this looks like. We might need more information. I might want to substitute in -0.5 or -1.5 or both. If I don't know what it looks like, plug in more points. So if we were to substitute in, sorry, just trying to make sure you can see, but also that I can write, f of -1.5 or -3/2, we're going to get a value at should be, I want to say -25 over -26. I can't read my handwriting. You know what? Let's do it. Oop, not that way. Let's do -1.5. Mostly because I can't read my handwriting. So going back and substituting in, I want to put this as -1.5 or as -3/2. I can replace that -1 with a fraction. Fraction. 3/2. Going back and replacing this -1 with a fraction. So there's -1.5. We get -20 over 21. Or if you want it as a decimal, -9.5. What I noticed from that is my -1.5. So over here, it is farther below. It is more negative. It is closer to -1. So this is lower. Over here. So now I can see that these 2 points are going to connect up and go this way. But I don't know if this side's going to connect up and go down or if this is going to go up. So we're going to have to test that too. So if we have points that we don't know, just keep testing them. -1/2 or -0.5. I think we should get -4/5. And -4/5 is lower. It's down here. So this one, when we plot it up, is going to look like this. It makes kind of a parabola here. So that one doesn't cross our x-axis. If we can't tell what's happening, plot up a point and see if we can figure it out. One last section to go. And you can do any of the points we need to between 0 and 2. We can do 1, we could do 1/2, we could do 3/2, we could do 2/3, whatever options you want to do. But we need to figure out a couple of values in there so that we can figure out what this is going to look like. So if we do our f of 1, actually get a 0 here. We get an x-intercept. We get a root. It's that 0 of our numerator where we're getting our x-intercept here. So this one is going to cross that horizontal asymptote. Since it's between vertical asymptotes, it's allowed to do that. We just need to figure out what's happening on either side of it. So when it's crossing that x-axis, when we have that 0 there, it's going to look a little bit more like a cubic. So we're going to need to do our f of 1/2. And we might need to do f of 3/2. You don't necessarily have to, but you can. So this one has a lot of plug and chug in it. A lot of type it into the calculator, simplify. When we substitute in our 1/2, we should get 4/15. And when we substitute in our positive 3/2, we should get, I believe, negative 5/26. If you get something different than that, let me know.
Negative 14
For which one?
3/2.
For 3/2, you got negative 4/21. Okay, let me double check this off quick. Just because sometimes it's that I just can't read my own handwriting. And I just want to double check before we commit to it. 3/2 to the third minus 4 times 3/2. Yep, you are right. I am wrong. Negative 4/21. Right with you. Between those two values, we can see that for our x being positive 1/2, us getting a positive value, positive 4/15, somewhere up there. Negative 4/21 is going to be over here. And that is more than enough information to figure out what this is going to look like. Because we know we cannot crash through these vertical asymptotes. Horizontal asymptotes in the middle, we don't have to avoid. Vertical asymptotes, we will not smash through. We are not the Kool-Aid man, we can't go through the walls. So this one is ugly and gross and probably the most complicated one that we have.
Are we gonna have something like that?
Not near that gross. No. Not near that gross. I would say we will have a rational function at least. It will definitely not have 3 vertical asymptotes. At most 2. We're mean, but we're not cruel. That would be cruel. Okay? So, working through these things, take a look at pieces, see what we've got. Tomorrow we're going to have the whole time to work on the review because our chapter test is coming up on Friday. So I'm putting up, this is all the numbers. This is 4, 5, and 4, 6, just because I know we went through 4, 5, and 4, 6 very quickly. So if you need another copy of the chapter review, those are right here. You need a copy of it? That one's unstable. I love that. So there's a few more up there. I'll make a couple more copies just because this one's unstable anyway. So I'll use it and make some more copies. But we'll have all tomorrow to work on it, ask questions, all that jazz. Chapter test is coming up on Friday.